Yeah, so basically, I'm going to be covering the sort of the technical architecture of FEVM, and also like why we built it, and all that stuff. So start off with, I'm going to go a bit back into looking at the FVM itself, for people who aren't familiar with how it works under the covers, before we then cover the EVM, and finally FEVM, what the hell this thing is. Okay, so fundamentals of the FVM. The FVM is built on a WebAssembly VM. Basically, WebAssembly is this VM that people have been building, this VM system people have been building for the web, but it's a VM that's designed for JITting or just-in-time compiling WebAssembly bytecode down to native code. The cool thing about WebAssembly for us is that we can actually take a contract written WebAssembly, instrument it with gas accounting, and compile that down to native code with the gas accounting in line. So it's really, really fast, even with gas accounting. The other nice thing about this VM is that it's bring your own language. So anyone can sort of build whatever they want in Rust or in Go in theory or whatever, as long as the language can then target WebAssembly. We've also built the FVM itself to be able to support multiple types of VMs. The EVM is the first one we're supporting, but the idea is basically like we have the FVM runtime underneath, or the hypervisor as we call it, and then you can run whatever VM you want on top of that. But because we have near native performance, this is actually not a huge issue. Like running a VM inside of VM is not a huge deal. But yeah, that's our goal here. And the other goal here is also like to sort of make the FVM really extensible, so you can sort of import your own addressing schemes, import your own custom account types, all this kind of stuff. We're still in the early stages of this, but we're like, it's looking pretty cool. Okay, so that's sort of the basics of the FVM, the fundamentals. The FVM is built around IPLD. So the state tree itself is an IPLD state tree built out of IPLD data types. The cool thing about this is it means everything is structured. And the other cool thing about this is it means that everything is Merkle linked. So basically, like I can take some part of my state and refer to it by CID. And then because everything in the FVM is built around IPLD, I can literally just send that entire substate. It could be very, very large, off to some other contract without having to copy it. I just have to refer to it by CID. They can then write within my state and maybe return something. So everything we've done is built in IPLD here. This is a quick diagram showing how this all works. Basically, a vector A with an IPLD state tree internally. It can then send an IPLD DAG to actor B with an IPLD state tree internally. Actor B can then return a state, some IPLD object or state tree or whatever it wants back to actor A. This is the architecture of the FVM. It's not like we don't have to go through this in detail, but basically, like we have this block execution that is for executing a single epoch. When we execute a single epoch, we create a quote-unquote executor. This executor applies messages on top of a machine. The machine represents sort of the current state of the FVM. Whenever we execute a single message, we create a call manager to manage like sort of the call stack of that one message. This call manager then manages these things called invocation containers. This is where we actually run the actors, and kind of like an invocation container runs some WebAssembly actor, which they can call back into this thing we call kernel, to then call back into the call manager to create another kernel, to create another invocation container. And basically this creates these sort of like processes all the way down, but you should think of invocation containers as processes. And this is how we sort of built the FVM. This part is not too important. I just showing this to you in case you're wondering how this all works. We can go over this more in the YAML later. But yeah. Okay, so that's the FVM. Most people here are somewhat familiar with that. Let's quickly move on to some background in EVM, because a lot of people here are very focused on Filecoin and may not know everything about how the EVM works. The EVM is a custom smart contract VM with 256-bit or 32-byte words. Most computers have 64-bit words nowadays, but the EVM went with 256-bit. This is a bit of a mismatch, unfortunately, because it means that like when you're trying to execute EVM bytecode on your native architecture, nothing matches. So it makes it a bit difficult, or very difficult, to optimize the EVM or to make a fast EVM. This is one of the biggest problems with it. The EVM, like so, in the FVM we have this IPLD tree under the covers that people use to store their state. In the EVM, actors get access to what is conceptually and sort of infinite, it's not really infinite, but almost infinite memory with memory with a 256-bit address space. Really, what this is a big hash map that maps 256-bit value or keys to 256-bit values. Under the covers, the EVM or this Ethereum, like it turns this into a Merkle trie, so it does turn it into a Merkle tree under the covers, but it hides this away from users. On one hand, this is nice because the users don't have to then think about how their data is laid out. On the other hand, it means the users don't get a chance to optimize their data layout. And it also means that there's no way for an EVM smart contract to sort of like refer to some subsection of their state because it's all mixed up together. In the FVM, we have a very clear like structure that the user can define for their state tree. Additionally, inputs and outputs to EVM contracts are just raw bytes. In the FVM, they're all IPv objects, but in the EVM, you kind of just pass around bytes, and you need to know what to expect to actually decode it. In the FVM, you don't like we do hide some of the type information because it gets expensive to just encode that everywhere. But on the other hand, like you still the structure is always encoded along with the data, so you can always decode data to something, or you can always decode data to the structure of the data and like understand it and explore it without having to like know the schema ahead of time. And finally, the EVM is interpreted in slow. The speed was basically just not factored into the VM design, and that meant that it's just actually not possible to optimize the EVM in many ways. Okay. However, the benefits of the EVM are ecosystem. So the EVM has this massive ecosystem with multiple smart contract IDEs, debuggers, tooling, all that kind of fun stuff. Multiple smart contract languages. So the primary one is still Solidity. There's browser integrations, chain explorers, and a ton of dApps. So this is really what we want. Building this out is very time consuming and requires a lot of money, a lot of people, and just a lot of community engagement. And we don't really have time for this. So this is where FEVM comes in. The idea of FEVM is to bring this entire ecosystem to the EVM, or sorry, to the FVM. So basically, we're implementing EVM on top of the FVM, and a bunch of tooling and like all these Ethereum concepts, so that we can literally just take things that have already been built in the Ethereum ecosystem and make them work in Filecoin. The tricky part is this means that we can't just have basic EVM bytecode support. We actually need support for the entire ecosystem. So we need support for Ethereum transactions. We need support for Ethereum style addressing. All this kind of stuff needs to behave the same way it does in Ethereum, at least from the perspective of Ethereum tooling. The tricky part is we also want to make everything Filecoin native. So we don't want to just have the Ethereum ecosystem and the Filecoin ecosystem. We want to have a single ecosystem that just happens to support Ethereum native tooling, but also works within the rest of the Filecoin ecosystem. We also don't want to supplant the FVM because we do like the ability to introduce additional VMs in the future. We do like working with IPv4 with the covers. This just gives us some features that you can't get on in the EVM. We do like the performance. So those are kind of the trade-offs we're going for here. To do this, we've compiled the EVM on top of the FVM, and we've introduced basically Ethereum compatible accounts and pluggable addressing. Unfortunately, right now, our Ethereum compatible accounts are hard-coded, so it is like a specific or EVM specific feature sort of built into the FVM for now, or to the FVM and to Filecoin clients. In a future upgrade, we have plans to turn this into full, it's called account abstraction. The idea is that users should be able to actually deploy their own custom account types. But unfortunately, right now, due to time constraints, we had to make this Ethereum specific. So that's the general concept. First part was building the EVM on top of the FVM. The EVM we built is actually just the EVM interpreter. It doesn't have all of the rest of the calling and everything else the EVM has. It's just the bytecode interpreter plus the precompiles. There's no special EVM support eventually, because we have some special support right now for Ethereum accounts, but that's the only special support we have right now, and that'll go away. It's also first class. FEVM or our EVM uses Filecoin and Filecoin gas. There's no EVM token or there's no ETH token or wrapped ETH or wrapped fill or whatever. It's just straight up Filecoin gas and straight up Filecoin. EVM smart contracts are top level Filecoin actors, so you can address them the same way you can address any other Filecoin actor, send funds to them, all that kind of stuff. And Ethereum accounts are also just top level Filecoin accounts that behave mostly like other accounts. There's some caveats. The final part here is that, again, we really, really want this to be Ethereum compatible. No bridges, no translations, nothing like that, which means we really need support for Ethereum transactions. So you can just take MetaMask and point it at a Filecoin client and make it work. And we also need support for Ethereum style addressing, which means basically I need to be able to sort of like derive an address the same way Ethereum would, maybe wrap it in a bit of Filecoin magic, and it should just work. Then it should be able to take a Filecoin address and then convert it into an Ethereum address. That is kind of the idea behind FEVM. The way we did this, the way we did the addressing at least, was to introduce a new address class called F4. You may have heard of this before. I've talked about it a few times. But basically, this lets actors on chain wrap Ethereum addresses in a Filecoin address, or really wrap any arbitrary addressing scheme in a Filecoin address by effectively delegating control of an entire address subname space to some actor. So in our case, we created this new actor called the EAM, or the Ethereum Address Manager, that manages the address namespace starting with F410F. So the EAM is this new actor deployed at address, or ID 10, which means it can control, if you read that text, it can control F410. In this case, you'll see that this text is talking about 1, 2, 3, 4. It's arbitrary actor, but in our case, we deploy the EAM at address 10. So it controls F410F and then whatever. The cool thing is it means that this EAM can literally just take an Ethereum address and embed it in a Filecoin address, just verbatim, and then pull it back out. So this means that we can compute addresses the exact same ways that they're computed in Ethereum, so that all the Ethereum tooling just works. Because often, like Ethereum tooling will take like an Ethereum key and then compute the address from that. We need that address to work the exact same way in Filecoin, or like they'll compute the address that should be computed from deploying a smart contract. And we need to compute the address in the exact same way. Otherwise, the tooling will expect one address, we will get another address on chain, and everything will break. So we have to make sure they get the exact same addresses here. Okay. The next part really was Ethereum accounts. So we've implemented a new Ethereum account, or native account type. This is currently, again, as I said before, special sauce. It's a special Ethereum account type that has some like special code paths in both Lotus and the FVM to make it work. In the near future, we are planning on migrating over to something we call account abstraction. The idea behind account abstraction is it should let anyone deploy any custom account type to the Filecoin network, and it'll just work. There'll be nothing special about the Ethereum account type. But that was more complicated, and we ran into a bunch of design questions we weren't quite comfortable with yet. So we punched that out to a future upgrade. Okay, that's kind of review. That's why I went really fast. We can also go over more parts of that later if you have more questions. But now I want to dig into the weeds of the actual FEVM architecture. Okay, so the FEVM is really composed of the two main things. There's sort of the EVM side and the Ethereum style account side. The EVM is really composed of two actors, the EVM actor and the EAM actor. The EVM actor is this new actor account that hosts EVM smart contracts. A single EVM actor is deployed per smart contract that's deployed to the network. So it's not like we have like one EVM actor for the entire network. Instead, like whenever a user deploys a smart contract, they get their own instance of the EVM actor. The EAM is, as I said before, just the address manager for EVM actors, and it's the actor that assigns addresses to these EVM actors to ensure they get a proper Ethereum style address. The Ethereum style accounts are how we interface with things like MetaMask. This lets us basically take Ethereum transactions and kind of like massage them into a Filecoin message, and then consume them on the network, so that you can just pull up MetaMask, use your some standard dApp, and then send a message from that dApp to the Filecoin network, and everything just magically works. I say this is also half-step account abstraction because we've implemented this with account abstraction in mind, but it's currently special casing the Ethereum account. Okay, first we put in the EVM. Again, it's a new actor as a sort of a minimal EVM interpreter. It doesn't have any special any gas counting internally, because it relies on native Filecoin gas accounting. It hosts a single smart contract, a single EVM smart contract, and it stores all of its state in something called a camped. This is a new data structure we came up with based on a hamped, but I'm not going to go into details because it's a bit complicated. Basically, we took a hamped, which is the standard sort of sharded map that we use to store Filecoin state, and then modified it to be optimal for storing expected EVM state. Mostly we optimize it for solidity. The basic idea here is that adjacent spots are stored next to each other in the camp, which means that if you when you load your smart contract, when you first load your state, you probably won't have to load any more state unless you need to load an entire array. And when you load that array, you'll load 32 slots out of the array at once, in sort of as a group, or which is more than 32 slots. But basically, it means that related state is stored next to each other, so it should reduce the number of reads and writes you have to perform. And finally, our EVM calls other contracts to the FVM. It doesn't handle cross-contract calling internally. It just delegates all that stuff to the FVM. Now I'm going to get into some of the specifics. Calling. So the way we've done calling is we basically, we call through the FVM. We've had to add a few features to the FVM to support this. First, we've added a read-only flag to send to support the EVM static call. EVM has this concept of static call where you can call into the contract, but prevent that contract from making mutations. We've added a flag that's going to read. Don't read to send. It lets you say, "Hey, this send is read only." Second of all, actors can now return error values on failure. In the past, FVM actors could only return values on success. On failure, they can just return a code. Now, on failure, they can return both a code and a value. This is because the EVM expects this and requires it. Finally, actors can specify gas limit when calling other actors. This is just required by the EVM. You need to be able to limit how much gas they can use. Okay. Precompiles. The EVM has this concept of precompiles. Basically, they're kind of like, the idea is that it's hard to implement certain operations in EVM efficiently, or they're just basically really expensive operations. So the EVM really wanted these to be implemented in sort of native code. The way we've done this is kind of like we've split it between like truly native code and WASM code. Because like WASM is much faster than EVM in general. So in many cases, we're able to get away with simply implementing this inside of the EVM actor instead of implementing it inside the FVM. In a couple of cases, we've delegated to the FVM, for example, like for signature validation and some hashing, we delegate to the FVM itself. But basically, we've implemented all of this stuff inside, or we've implemented the precompiles themselves inside the FVM, inside the EVM actor. Then those precompiles will occasionally call out to the system to the FVM to perform some really expensive operations. So some of the limitations here, unfortunately, one of the limitations here is that there is no way to limit the gas used by a precompile in FEVM. So in the EVM, you can call precompile and you can say only use X amount of gas, and that precompile will return immediately if it would require more gas than that. In the FVM, because we don't have, or in FEVM, because we don't have EVM specific gas accounting, we just have FVM gas accounting, and because the EVM precompiles are implemented inside the EVM itself, we have no way to limit the gas. So you might run into situations where you try to call to some precompile, and it you would expect to see an out of gas error on failure, and it'll just fail your entire contract. This is not great, but this is a trade-off we have to make for performance mostly. So those are the precompiles. Something I didn't mention in the slide, but it's also important, is we've implemented a bunch of FVM-specific precompiles. If you're trying to use precompiles, you should probably use them through Zondax's Filecoin Solidity library. But basically, if you want to call a native smart contract, you should be using one of the FVM precompiles called call actor. This lets you it lets you call a native actor with the sort of the native calling conventions of the EVM calling convention. So if you call using the call opcode in Ethereum, you'll call with the EVM calling convention, and it will actually invoke a special method called invoke EVM. But if you call through the call after precompile, you can invoke any arbitrary method you want, almost any arbitrary method you want, with arbitrary parameters on any actor you want. So that's a bit of a side there. Okay, events. We implement events by adding event support to Filecoin itself. Filecoin events don't quite look like Ethereum events. Filecoin events are more like structured logging, where each event is basically a tuple or a list of key values. This is, again, how structured logging works. We generally have keys, or just a bunch of key value pairs. We've then implemented EVM events in terms of this. So an EVM event will generally be K1 first key, K2 second key, et cetera, up to 4, or 0 to 4 keys, because that's how Ethereum events work. And then finally, there's a V mapped to a value to store the Ethereum logs value. We additionally store some flags that can tell the Filecoin client whether or not event needs to be indexed and stuff like that, but it's not too critical here. But the important thing is we do support events. We just encode them slightly differently because this is just more flexible. Yeah. Okay. Delegate call. This is something you may run into as well. The EVM has this concept of delegate call, where you can basically call some other actor's code into a context. Basically, this would run someone else's code as you. The FVM implements this by basically just reading in the target actor's code into your context, and then the EVM actor will call itself with that code and execute that code in its context. It's a bit funky because there are the two funky parts about this. One, we do have to call into the target actor to get its code, but we don't actually ask the actor to run anything because the actor is not running in the right context. The other funky part here is you have to then do a self call. The self call is required to limit gas and sort of create a failure domain. Because basically when you do a delegate call, you expect that any failures with the delegate call can get caught by the caller that is performing the delegate call. So that's why we need to do a self call here. But this delegate call method is special because it can only be called by yourself. So basically, when you invoke the delegate call instruction, the EVM actor will delegate call itself with the target bytecode. But if you try to call the delegate call method on some other actor, it'll just say, no, you can't do that. That's not how that works. Okay. Finally, create and create two. This is where a lot of the complexity of the FEVM comes in to play, because create and create two need to be able to assign Ethereum style addresses to Filecoin actors. And the important part here is we really wanted these to be native Filecoin addresses. We didn't want them to be some sort of separate address type. So to do this, we had to introduce this new address class called F4. We talked about this a bit. But basically, we use this address class to embed Ethereum style addresses in Filecoin addresses. So to actually create an actor, there's this whole complicated diagram here. Contract A, the bytecode in contract A will say create. Contract A will then call the create method on the EAM actor. The EAM actor will then call something called exec4 on the init actor. Exec4 is the method we use to create new actors with F4 addresses, or with addresses in the F4 address class. So basically, the EAM will call exec4 on the init actor with the address that it wants to be assigned, that it wants to have assigned to this new contract. The init actor will then construct this new contract, in this case, contract B. Then it'll sort of go back up the call stack and return the address to contract A. So this is how we've implemented create and create two. One of the cool things about this is that, or not the cool things, one of the important things about this is that this final step, when we construct the actor, it can actually replace a placeholder. So the placeholder is this new concept being introduced with F4 addresses, where if you send funds to an F4 address before there's an account or a contract or anything deployed at that address, it'll automatically create a placeholder just to hold the funds. This allows you to send funds to an address where you expect the contract to be deployed before it's actually deployed there. Create and create two can then actually deploy a contract over a placeholder, and that new contract will now inherit the funds from the placeholder. Okay, Ethereum style accounts. This is the final component. I'm sorry, this is taking a long time, but there's a lot of pieces here. Ethereum style accounts is this new account type we've added to the FVM and to Filecoin in general. Basically, the way these work is if you send funds to an F4 address that doesn't have any account there, it doesn't have an account system marked up or anything, it's empty, it'll create a placeholder, as I've already said. Then what you can do is you can treat that placeholder as an account and try to send a message from it. If you successfully send a message from that account, because you've signed this message correctly, such that the message would have been correctly signed if an account had been deployed to that address. The FVM will then automatically deploy an account to that address for you on first send from that address. This is really confusing, and I apologize for this. But another way of thinking about this is basically when you first try to send from an address from a placeholder, when you first try to send a message from a placeholder that doesn't have an account there, just a placeholder, the FVM will effectively temporarily deploy an account there, validate that the address was valid to be sent from that account, into the account there, validate that the address was valid to be sent from the ETH account, and then if that validation, or if it was valid to be sent from the ETH account, it will then leave the account there and process the address. If it wasn't valid, it'll say, well, the message wasn't valid in the first place. This is kind of a half step towards something we call full account abstraction, but it was necessary. Honestly, I would say it's necessary, but we actually want this to go away in the future. We want to have this account deployed on first send to an F4 address. So in the future, we'd actually change F4 addresses such that when you send a message to an F4 address that doesn't have any actor deployed, instead of deploying a placeholder, we'd actually automatically deploy, in the case of the EAM or the EVM, we'd automatically deploy an ETH account. But that's getting into really complicated territory, so we won't get into too many of the details there. But that's Ethereum style accounts. I guess one final thing I want to mention in terms of Ethereum style accounts is how does it interface with things like MetaMask. Basically, MetaMask will send an Ethereum transaction to the MetaMask will submit Ethereum transaction to Lotus. Lotus will then sort of massage this Ethereum style transaction to make it look like a Filecoin message, and that Filecoin message will be submitted on chain. Lotus will then, when it's validating that message, it will then turn it back into Ethereum style transaction and validate the Ethereum transaction signature over that message or over that Ethereum transaction. And if that checks out, it'll say this is a good message. Currently, this is implemented entirely in terms of special sauce for Ethereum transactions. In the future, instead of doing this validation inside of Lotus, we actually want to do this validation inside of the Ethereum style account actor itself, where basically like Lotus would pass the entire message to the Ethereum style account, and the Ethereum style account would validate the message and say whether or not it's valid. This is what we call account abstraction. It basically lets users deploy new account types that can validate their own messages instead of relying on predetermined validation rules implemented by Lotus. So that's all I have to talk about. I apologize that there was a lot of technical details here and they're very complicated, but I'm hoping that at least gives people a starting point to ask questions.
Thank you, Steb. Cool. So the good news, the bad news is maybe we're a little tight on time. The good news is you covered a bunch of the stuff that I already covered, that I wanted to cover. So we can move fairly quickly. Steb will not coordinate our presentations here, but it's fine. And that's actually a good segue in that what I mostly have, at least after stripping some stuff out, is basically a bunch of FAQs that I think that we've already been kind of getting. Whoa, that is much bigger than I wanted it to be. Zoom out, damn it. Okay, fine. Oh, God damn it. Let's go with that. Okay, that's fine. Mostly wanted, I wanted to cover some questions that we've already kind of been getting from users, node operators, integration partners that we've been talking to. Some of these are questions that I'm kind of guessing that folks here on the call will already have, and I try to preempt them. Others might be questions that the folks that you work with or talk to every day might start asking you. And so I wanted to quickly go over some of those, and then have as much time as possible for Q&A from folks here. The AMA format. So yeah, some quick ones that I wanted to cover. If I'm born and raised in the Ethereum ecosystem, Lotus and Filecoin confuse me. How can I orient myself? This is one that I'm kind of imagining people will have, because mostly we're talking to folks who are actually familiar with Lotus, kind of the opposite side of this. But one of the things that the entire FEVM effort really centered itself around was to build basically as much compatibility with the Ethereum APIs, or like the popular Ethereum APIs of tools as possible. And this now lives in Lotus today, which is great. So if you are someone, or you're talking to someone that's familiar with that side of things and are interacting with a Filecoin node or a Lotus node, as far as possible, we've kind of matched behavior with Ethereum. This is imperfect, partly because it is a work in progress, but more also because there are just some Ethereum concepts that do not translate into Filecoin. So there are kind of like things that lay unimplemented. But for the most part, I think this we try to make it as easy as possible to not have to worry about kind of things like chipsets or kind of core Filecoin protocols that are more complicated as you get started with in Lotus at least. Opposite kind of on the opposite side of things, if you're a storage provider who's already been around the Filecoin network for however many years and just haven't been motivated to care about the FEVM yet, what's going to change for you? This is one we've gotten a few times. Basically nothing. Your node is not going to get slower. Your storage is not going to significantly increase. We try to make the FEVM related changes in Lotus as opt-outable as possible. And so if you just don't care yet, or you want to consume the changes slowly, the day of the network upgrade, pretty much nothing will change for you in terms of your day-to-day operations. In particular, core storage provider operations will not be getting more expensive in terms of their gas costs for the most part. This is a little bit of a difference from the NV16 upgrade that we had back in June, where things did get more expensive. The one wild card is kind of the base fee and how chain activity is going to change. If we do wind up having more competition for chain throughput, then the base fee goes up and overall operations go up. But that's not really an FVM specific change as much as the Filecoin network maybe gets busier. But we really don't know how this is going to change. It might be absolutely nothing. It might be a noticeable increase. Hopefully not a decrease. I'm interested in building dApps that interact with the Filecoin protocol. How can I do this? So what I meant by this is basically if you are familiar with some of the bones of the Filecoin protocol today, or you're interested in interacting with them in your dApp, whether that's deals or you're interacting with storage miners because you want to build a lending pool or some kind of oracle that has information about the current Filecoin state. What we did was basically expose as much of this as we thought was useful and safe to expose in a set of new APIs that the built-in actors exposed to contracts. And the FVM team worked with the Zondax team to also produce a bunch of libraries that smart contract developers can use to get this information. These are mostly getters. So it's kind of, so you as a smart contract developer, your immediate kind of point of contact there is the fill.sol libraries from Zondax that can expose a lot of that information to you. Cool. I think I've only got a couple more. I can't do the thing I want with the FEVM because of a limitation in the FEVM itself, in Lotus and built-in actors. What do I do? Let us know. Issues welcome on all of those repos. We were as far as possible, we tried to get user feedback. I'm saying we, really, the FEVM team, try to get user feedback in order to build something that would be immediately useful. But there's definitely going to be missing pieces, whether that's kind of the core side of things or maybe just the tooling that Lotus exposes or something like that. So we're really hoping that we get a wave of feature requests, maybe bug reports or just like enhancements that folks really want because what we released yesterday isn't quite there yet, and we're explicitly dedicating time to kind of address some of those and be able to build some of those out. So all that to say, feedback very welcome. If you already have that, please let us know, and if you start to receive that from folks that you work with on March 14th, let us know. This is a quick one I wanted to throw in. I'm a node operator who had a rough time during the Shark upgrade in November. How will this upgrade be? So this is really related to the upgrade day itself, or the hour when the network upgrades. Short answer, it should be totally fine. The Shark upgrade back in November was far and away the most complicated migration we've ever done in Filecoin. This will far and away be one of the easiest ones we've ever done in Filecoin. So we're expecting the migration to take less than a minute. We're not expecting any null chipsets. So you should be good, is essentially what I'm saying. No promises on future upgrades, but this particular one on March 14th should be okay. When does all of this go live? March 14th, as I've said many times now. Lotus 1.20 was released yesterday. If you are running a Lotus node, you have until March 14th to upgrade. Please upgrade sooner if you can, and give us feedback if anything isn't quite working. Cool. Those were all of the FAQs that I kind of wanted to blitz through. We have basically 15 minutes for questions from anyone. So I will stop sharing. And I think folks can just unmute and ask if they have questions. We have many folks from the FVM team here who will definitely be able to answer them, in addition to Steph and myself. And thank you all. And thank you, Jennifer, for organizing this. Patrick has a hand. Let's go.
Yeah, I can kick us off. So I'm new to all this FVM stuff. Super interesting to look at this. My question is, if I have an EVM contract, got a Solidity contract, how much kind of tinkering and shimming and tweaking do I have to do? I guess maybe just like roughly as a percentage of your code to get it to fit with some of these things that Steb was talking about.
So ideally, very little. The main things you might need to do are remove any gas constants. So like the gas on the FVM will be completely different than the gas in the EVM. So if you happen to have hard-coded gas, which you shouldn't have done, but you did, then you'll have to deal with that. That's the main thing you'll have to deal with. The gas stipend, well, first of all, there really is no gas stipend for transfer. Instead, we just automatically give it a gas limit of 10 million gas, which is a lot. If you were trying to rely on transfer to, for example, prevent like recursion or anything like that, or like reentrancy issues, your contract was already broken, and you shouldn't do that. So that's basically the answer there. But in general, like there are a lot of little gas-related things. Also, as I said before, precompiles, we don't limit the gas when calling precompiles. Which like the user-specified gas limits don't apply when calling precompiles. So if you do call precompile with untrusted inputs, you need to validate those inputs first to make sure that they wouldn't, for example, like cause any problems or make you run out of gas. If you care about that, if you don't, then you'll just run out of gas. That's fine. But yeah, so it's a lot of stuff like that around gas. That's for porting. I think there's something else. Gas usage will be different. So like the instructions will again, as I keep on saying, charge FVM gas, not EVM gas, which means that the actual cost of different instructions can be wildly different. So for example, if you're using like an EVM specific gas optimizer, there's a fairly good chance that it'll come up with the wrong code. So this is actually a problem we're probably going to run into in the future. We might want to like see if there's any kind of profile guided optimization we can give to users to target the FVM FVM instead of the EVM. This is probably going to be a bit difficult, but basically, again, the gas pairs are totally different. So if we're trying to like optimize for like basically we're trying to make something good would be optimal on the EVM, it is not likely to be optimal on the FVM. But yeah, that's the main thing I can say.
Yeah, I think those are good exceptions to call out, but I think for the most part, at least for the high level answer to the question, Patrick and Ro, feel free to correct me if I'm wrong. The answer is basically nothing, and that was very much the intention of the FVM.
Yeah, that's basically it. Yeah.
Thanks, guys.
I would add to that saying that things that like part of this upgrade was also involved implementing features that we didn't have in the Filecoin protocol ahead of before FVM itself, like for example, actor events and actor logs, right? We didn't have this feature in the protocol. It was always intended to be there, but this acted as a forcing function for us to implement those features so that we could then use those features to cover Ethereum logs and be able to emit Ethereum logs in a way that is fully compatible with what tooling also expects in the same format as they expected on.
More questions? I know people have them.
In terms of running Lotus, I had the impression that before this, if you want to do things that affect the chain, if you want to do things that affect how much compute every node in the network or every Lotus node need to do on every epoch, you would essentially have to set up a storage provider or something that interacts heavily with the network, short of just sending transactions. It seems that now creating smart contracts, it's something that would be much easier for people to do. Are we expecting, I don't know, the amount of compute or RAM usage that Lotus is using on every epoch to go up? Are the minimal requirements changing? I understand, of course, if everything will be mediated by the fees and so on, but in general, what do we expect?
No, so the gas limit is fixed, basically. So there's a maximum 10 billion gas that can be at any block. There's a target 5 billion gas per block. So basically, like, due to chipsets and all whatever shenanigans, we expect around 20 billion gas per epoch. That's 20 billion nanosecond, or sorry, no, that's it's 10 gas per nanosecond. So that's 2 billion nanoseconds. So basically, that is the sort of the target block time. And that doesn't, like, it doesn't matter how much people are using the chain. The more people use the chain, the higher the gas price will go. It won't actually let us have more execution time. As a matter of fact, though, like right now, the vast majority of the gas usage, or not gas usage, sorry, the vast majority of the block time is taken up by cron, not by normal chain execution. And smart contracts should not be impacting cron. The thing that impacts cron is storage providers. So like, basically, there's no way for users to really, or sorry, there should not be a way for users to slow down the chain here unless we've made a terrible mistake, which we might have. And if we did, we've made a bug and we have to go fix it. But we've gone and actually like rebalanced some of these gas values to try to avoid this. But yeah.
So yeah, so in terms of sorry, go ahead.
What about memory or a space, disk space?
So memory, we have set a 2 gigabyte limit on the amount of memory that can be allocated sort of over our entire call stack. This is actually vastly more than the amount of gas available. So you should never really hit this, as far as we know. There's also, again, call stack limit, which limits the number of EVM actors you can sort of spawn. In terms of disk space, this is a concern. Where like now users can just sort of store arbitrary things, and they do have a reason to do that. We have increased the storage cost slightly, but it might not have been enough. So we do have concerns there. If this turns out to be a problem, then we will have to like basically just massively increase those costs. We will probably have to find, if we do that, we'll probably have to find some way to discount those costs for native actors. But we'll have to figure that out. Right now, we've increased the cost from, I think it was 1,300 to 20 something. I can't remember the numbers, but yeah.
Yeah, I don't know the exact numbers either. Yeah, so I agree with Step here. I think the short answer is compute time and memory are very much things that are well bounded and basically should not change very much, if at all. Storage is a little, because, you know, even though there's new things you can do with the Filecoin network, there is still that hard limit. Storage is a little bit more of an open question. It's obviously still charged for with gas, but yeah, as there are now users who are actually, there's this new way to use Filecoin, as you said, who are going to be deploying contracts, and those contracts will have their own storage associated with them, that might start to increase. Again, they'll be paying for that storage with the gas model, but that might be a change in behavior that we'll be monitoring for, basically.
Yeah, I will add something to that. And the storage footprint is also somewhat correlated to the memory usage, to the long-term memory usage of the node, because as you know, Lotus uses Badger, and Badger keeps indices in memory and so on. So we do expect a increase in the state footprint, which can also translate into a growth of the indices that the node will need to track, which can then translate into a higher memory usage. But we'll need to keep an ime on that.
But if those are memory mapped though, so they can be
the
flushed.
value logs are. Yeah,
I believe they're both memory mapped.
I'm not convinced they are.
Okay.
Yeah.
Badger will get very slow.
Yes, that.
Yes.
I think we're still. I mean, we're still not there, but I think at around 1 terabyte of Badger storage, things will start degrading more heavily. Maybe I don't know what it's doing from that point.
LSM, yeah, because it's an LSM tree. Like there is definitely a threshold there in which the tree will unfold another level, and like things will get exponentially worse.
That is a concern we have. Like honestly, like if it starts looking like that's a reality, I think we will need to push towards using something other than Badger, at least in some ways, because like for a lot of the state, it's kind of sitting around all the time. So we could probably have a data structure that's better optimized for reads. The other part here is like we will probably want to have some form of concept of rent that we haven't really figured out yet. I really wanted to get this done before we launched programmability, but rent is really complicated. Yes, we can expect like if this becomes popular and if people store a lot of data, we can't expect changing snapshots to increase its size. Yes.
I have another question in terms of, because part of the creating the change snapshot is traversing the state and following IPLD, and I don't care if it's a HAMT or a CAMT, I guess.
Mm-hmm.
Does the user or the smart contract creator have any control over the underlying IPLD structure, like ability to add nodes with custom hashing functions or something like that?
No. So that's the goal for M2.2. But when we do that, we have to then carefully consider the structure and layout that we allow, instructions that we don't allow. Right now, no. Right now, they're limited to a camped. This camp has some optimizations to ensure that we don't have like really deep data structures as well.
Thanks.
Thanks. And that is a really good question. Who has more questions? Yeah, Jennifer says 5-minute check in Slack, in chat.
I was just going to answer the question, Johnny's question. So I'll just basically, Johnny's question is FEVM always going to support future EIPs, or is it going to pick and choose what we want to support? The answer is basically we are not tracking Ethereum as a network, and many of these EIPs have to do with changes in Ethereum as a network. So things like gas costs and things like, for example, introducing new transaction types and so on. We will evaluate those carefully and determine if they in a way affect the ability to deploy Ethereum smart contracts and modern Ethereum smart contracts to Filecoin. We will need to evaluate those EIPs, but in general, the policy is, say, for example, there's an EIP that introduces a new opcode. That opcode then gets used by the Solidity compiler to produce bytecode that uses that opcode. If we don't support that opcode, that would mean that those modern contracts that are compiled with modern versions of Solidity wouldn't be supported in Filecoin. So those are the kinds of EIPs that we probably want to implement. But if it has something to do with kind of like, gas fees or state or data structures within Ethereum itself, it would not be relevant for us.
For some concrete examples here, we don't implement sort of the hot keys and cold keys. Because we don't do Ethereum gas or anything like that. We might eventually try to find some way to re-implement this kind of concept in Filecoin, but that would be a Filecoin specific thing. We also don't we did implement push 0 at the last minute, and we did change block difficulty to pre-ran DAO to follow the EIPs there.
I have a follow-up to that. I'm curious, do we know how frequently Ethereum, or rather the EVM itself, makes changes like that? And say in the past couple years, how many opcodes have they added or changed behavior of?
So it changes. It's highly variable. Not really. It doesn't change that much because, of course, they need to keep backward compatibility always, right? So this is always kind of the more features the EVM has, the more backwards compatibility they have to worry about as well. And kind of so it's not that frequent. There are changes. There are new, for example, there's the proto-dank sharding EIP, which we likely won't implement because it introduces a new transaction type, but then it also introduces an EVM opcode that is only used within specific contexts where you want to commit data blobs from shards into or rollups into the Ethereum chain, and that is very much Ethereum network specific. So we don't expect users to deploy those kinds of those kinds of contracts into the network. I will say that our end goal is always to enable the seamless portability of contracts, of smart contracts that are generally dApps, right? To Filecoin, things that are for example, rollups for Optimism or Arbitrum, and these docking contracts are those rollups are specific to Ethereum. So porting those contracts, which in the future will use proto-dank sharding, for example, doesn't really make a lot of sense for Filecoin. Where those networks, the equivalent of those networks in Filecoin is actually going to be facilitated by IPC, by interplanetary consensus. So we'll have our own way of creating rollups and sidechains and subnets.
I think we can take one last question from folks. No.
One has any questions? I have one last frequently asked question. This is around F4 addressing. So like frequently I hear people say like with calling Ethereum accounts and EVM actors F4 actors. I want to make sure we don't do this because in the future there will be other actors with F4 addresses. We can say F410 because all these actors will have an address starting with F410, but F4 just means delegated. So like, for example, F420 might refer to some other address manager deployed at address 20 that decides to compute its addresses in some other way. Yes, we almost made that the Ethereum address.
We're very close to. I think it was actually part of the initial specs.
Okay, we're at time. Thank you everyone for joining. Thank you, Steb and Aayush, giving an amazing presentation, walks through on how FEVM and the lotus-dev works. If you have more questions, you know where to find us. And I hope everyone here finding this like useful. Thank you for joining us on this No Meeting Wednesday, and have a nice one. Bye.
And thank you, Jennifer, for putting this together. Yeah.